Okay, YouTube, in this video we're going to do a brief run through of how you might necessarily sketch a polynomial function if we know the function itself. And basically it comes down to three simple things that we tend to do, and these things are listed here. We say, first of all, we're going to determine the end behavior of our graph. What we know, at least at this point, hopefully if you're watching this video, is this, that all polynomial functions are everywhere continuous, but it is the case that either we have a graph that starts down on the left and then does some stuff in the middle here and then maybe goes up on the right. We have a graph that could start up on the left and then do some things and maybe go down on the right. Or we could have our end behaviors be the same. We could say start up, do some stuff here in the middle and end up on the right, or maybe start down here on the left, do some stuff in the middle, but also end down on the right. So we could determine end behavior. Then after that we're just going to plug in some x values and find some y values on our graph, and then the third step is just this. We're going to draw or sketch a continuous curve from left to right through our points. So that being said, let's go ahead and get started by taking a look at this function that I've listed up here, f of x. Okay, so we say f of x, or y, equals negative x to the fourth minus 2x cubed plus 2x squared plus 4x. And one thing I suppose we could point out is this. Technically, this is written in standard form because our exponents are going in decreasing order, but you'll notice here that we're missing a constant term, which actually does come into play when we evaluate this function synthetically. So let's start with end behavior. We say end behavior, 1. We want to know as x gets really, really small towards the left, what do our y values do? And as x goes to the right, what do our y values do? So we notice here that our degree, this is a 4th degree thing, which is even. Which, if you look back down here at these 4 possibilities, we say it rules out these first two because anything with even degree must, it must start and end the same on the left as it does on the right. Furthermore, we can see up here, we say we've got a negative leading coefficient. And that negative leading coefficient, guarantees one thing, and it guarantees that our graph eventually ends down. So we'd say this is our winner right here. Essentially, we say we already know about our end behavior of our graph that I like to put this in here. We say it starts down and it ends down, and that's what we know about it. So moving on from here, that's our end behavior here. We say as x goes to negative infinity, our f of x values, our y values, apparently approach negative infinity, and as x goes to positive infinity, we say our f of x values also go to positive infinity. So now let's move on, let's plug in some x values. And so in terms of what x values to plug in, I think it's very, very clear that, x values around the origin are going to be most convenient here. Now, the thing is, plugging in x values into a function like the one I've listed here, which is negative x to the fourth minus 2x cubed plus 2x squared plus 4x, by direct substitution tends to be a pain in the neck. So, we're going to use what we call synthetic substitution. Before we do that, however, I think it'd be nice to point one thing out. Plugging in 0 into a function makes any x value that you had basically drop out. So plugging in 0 for x means that the only term that matters here is our constant term is 0. So what we've already determined is this. When you plug in 0, you get a y value of 0 because every term had an x in this function, and so you get a y value of 0. Let's move on. Let's plug in, say, 1. So we want to find f of 1. So we say f of 1. Now the thing about synthetic substitution is this. The x value that we're plugging in goes on the outside of our array, and on the inside of this array what we're going to do is we're going to plug in all of these coefficients that we have in our original function, including any that are missing, which in this case we were missing a constant term of 0. So we say negative 1, negative 2 x cubed plus 2 x squared plus 4 x plus 0. So now the way synthetic, of course, works is this. You begin by dropping down your leading term here. But we'd say we'll multiply this by the number that we're evaluating for, which is out here is 1. So 1 times negative 1, we get negative 1, and that goes up in our array. So now we're going to add these two numbers here, and we get negative 3. And now we're going to take this negative 3 times the 1 out front here. Negative 3 times 1 is negative 3. So we're going to add these now. A positive 2 and a negative 3 gives us negative 1. Negative 1 times the number out front times 1 is negative 1. Negative 1 plus our 4 gives us 3. 3 times 1 is 3, and then eventually we say 0 plus 3 is 3. And the significance of this point right here, or this number right here, is this is our f of 1. That's our function value at 1. So we'd say if I was going to graph this, I'd say, okay, well then x is 1. We get a y value of 3. So that's nice. How about 2? What if we plug in 2? So now, again, we're going to drop in our numbers into our array, -1, -2, 2, 4, 0, and we'll put a 2 out here, 2. So now, carrying this down, we say -1 times a positive 2 is -2. -2 plus -2 is -4. -4 times a positive 2 is -8. -8 plus a positive 2 is -6. -6 times a positive 2 is -12. -12 plus a positive 4 is -8. And then if we double this -8, we get -16. When added to the 0, gives us -16. So basically here, we say at an x value of 2, we are clear down here at -16. And just to kind of, exaggerate this, we say, well, we'll call this like -16, down here. Okay, so let's plug in -1. We'll plug in a few more points here. -1. So -1 going into our array, we say, putting back our coefficients, -1, -2, 2, 4, 0 from our original polynomial. And we're plugging in -1 now. Let's go ahead and carry out our synthetic substitution. So we get -1. -1 times -1 is 1. 1 plus -2 is -1. -1 times -1 is 1. We get 2 plus 1 is 3. 3 times -1 is -3. Plus our 4 is 1. 1 times -1 is -1. And -1 plus 0 is -1. So we say when x is -1, we are at a height of -1. Okay. When we plug in -2, moving right along, -2, let's put our numbers back into our array. -1, -2, 2, 4, and 0. We're plugging in this time -2. So let's carry this out. We get -1 times -2 is 2. 2 plus -2 is 0. 0 times anything is 0. So this plus our 2 is 2. 2 times -2 is -4. -4 plus positive 4 is 0. This times 0 is 0. And 0 plus 0 is 0. So the interesting thing is our graph is at a height of 0 here. So far I could say, well, from left to right, if I were to sketch this, I could say it's a nice smooth curve that goes through these points and might look a lot like this, which kind of reinforces the fact that it ends down on the right. Now you'll notice on the left here, it kind of started as we go from the right to left to go up again. So it is worth our time to actually plug in -3 to see what it does a little bit to the left of this. But at -3, let's go ahead and try and squeeze this one in up here. We say -1, -2, 2, 4, 0, our coefficients from our original function. -3, so when we put down our -1 here, we say times -3, we get 3, plus our -2 is 1, times -3 is -3, plus our 2 is -1, times -3 is +3, plus our 4 is 7. 7 times -3 is -21, and -21 plus our 0 is -21. So basically, we are clear down here now. So basically, it just means our polynomial falls to the left like this. And so this would just be a sketch because it gives us a rough idea of how to do this. But basically, to reinforce what we're doing here, again, we just find the end behavior. We said it started down, ended down, which was totally reinforced by what we found by plugging in extra x values. You notice we did a lot of plugging in of x values using synthetic substitution. So the last thing I wanted to do was this. I actually wanted to type this into a graphing utility to observe what this would look like. So we say, okay, we had -x to the 4th minus 2x to the 3rd plus 2x squared plus 4x. And we get this function right here that when looking at this, okay, we can make this a little bit more vibrant, if you will. Take a look at this, and we'll go back to our sketch. You notice that they're very, very much the same, or at least similar. Okay, so that's the general gist of how you sketch polynomial functions.